Welcome everybody. This is Raiyyan Malik and I am presenting my poster on X value equivalence checking of digital circuits using Boolean Satisfiability Techniques. Equivalence checking is a formal verification approach in which the verification is done using mathematical methods and equations. One of the key challenges of verification is the presence of X values, which can be introduced due to the low power systems including the power gating. In my project, the X values are injected using the DC gate. A DC gate is a three-terminal device having an input, an output, and an enable signal. When the enable is 0, the DC gate acts just like a buffer. When the enable is 1, the output is non-deterministic. That means it can have a value 0 or 1. So we treat it as X value. As now we can have a 0, 1 and x in the netlist, so a standard binary logic will not work. So we require a three-valued logic in which the logic 0 is treated as 0 0, 1 as 0 1 and x as 1 0. This problem statement is taken from IC-CAD 2020 CAD competition in which there is a constraint that the netlist cannot have a z value. So we can treat the z value as 1 1, but it is not used. So every logic gate is encoded with this three-word logic by taking MSB and LSB separately. The final formula at every primary output is converted to CNF or conjunctive normal form using Seaton transformation. In standard problems, the meters are created using the XOR gates, where the one input of the XOR gate is the primary output from the golden netlist, and the other input is the respective primary output of the revised netlist. But due to the three-word logic and presence of the X values, a normal XOR gate will not work. So we require a compatible equivalence gate to check for the equivalence including the X values. A compatible equivalence gate is formed using these formulas. So for every meter, the XOR gates are replaced by this compatible equivalent gates. Now let us talk about the SAT framework. First of all, we have two netlists. One is golden and another is revised. We need to check for the equivalence between them. There are two constraints that no Z value of floating signals can appear in the netlist, and only 0 and 1 can appear at the primary inputs. Now first of all, we pass the golden and revised netlist, and for all the primary output pairs we create the meters. Now for the final formula we OR all the meters, and the final formula is fed to SAT solver. After that, the SAT solver is invoked, and if there is a satisfying assignment is found, then we report that both the netlists are non-equivalent. And otherwise, if the SAT solver is not able to find any satisfying assignment, then we say that both the netlists are equivalent. In this algorithm, we are giving bare clauses to the SAT solver to solve without any optimizations. So in order to optimize these clauses, we need a new framework. So SMT framework is designed. In the SMT framework, first we parse the golden and revised netlist. After parsing, constant bit vectors are defined. These constant bit vectors are defined for our three-variable logic. For 0, 0, a constant bit vector 0 is defined. For 0, 1, a constant bit vector 1 is defined. For 1, 0, a constant bit vector x value is defined, and 1, 1 is not used. After this, we form the expressions. These expressions are the Boolean and logical expression for all the gates. So these expressions are from going from primary input to primary output. After forming expression for all the primary output pairs, the final expressions are fed to SMT solver to solve. The SMT solver does some pre-processing like substitution, variable elimination, and reduction. By, by experimenting, I found that the SMT solver reduced the complexity of the problem in two ways. It can introduce more number of variables in order to make the problem easy, and thus increase the number of clauses, or it can reduce the number of variables and thus reducing the number of clauses in order to make the problem easy. After this, the final clauses are fed to SAT solver to solve. If a satisfying assignment is found by the SAT solver, then we report that both the netlists are non-equivalent. And if a satisfying assignment is not found, then we report that both the netlists are equivalent. To compare SAT framework with SMT framework, we use SAT time. SAT time is the time taken by the SAT solver to solve the clauses. Now, non-equivalent cases cannot be used to compare because if the SAT solver finds a satisfying assignment luckily or before, then the timing will be less. So equivalent cases are used to compare the SAT and SMT, and we can see that there is not much difference between them. And for only the SAT framework is able to solve one case extra. Due to this, we can conclude that SAT-based framework is marginally better as compared to SMT-based framework. But the SMT-based framework can be further improved by doing optimizations. Further improvements can be achieved by circuit partitioning and reducing the subspace. Thank you for your time.